So from Auckland, so very strange accent when you speak English, at least for me. But he's going to talk, and forgive me, what is LIBS? You have to.
I'm going to explain that. Yeah. So I've been looking forward to getting my hands on this PA system. The reason for that was that when I was a teenager, I worked at McDonald's, and one of the jobs I had was working in the drive-thru. And I worked out that if I lowered my voice low enough, that I could get a reverb effect going on that would vibrate through everybody's headset and annoy the hell out of them. It kind of backfired on me one day because a guy turned up at the drive-thru window and he said, "Well, based on your voice, I expected you to be stripped to the waist with brass rings through your nipples." I said I was sorry to disappoint him, but would he like fries with his order? It's enough silly stuff. So I'm kind of happy to be talking about this today. For the longest time, I reckon for about 5 years, I've been giving grumpy old man talks. And I'm going to blame Marianne Scherps for that, and maybe Franco Tironi, because they made me come to EAFS, and I said, "Would you like to hear about new science, or would you like to hear about the state of the field?" And they said, "I would like to hear about the state of the field." So I've been for the longest time giving grumpy old man talks. They're immensely amusing for the audience, but they're not particularly fun to prepare. And I'd rather be doing what I'm doing today, which is talking about fundamentally new science. So I'm not going to be talking about likelihood ratios, I'm not going to be talking about interpretation, I'm just going to be talking about a little bit of statistics, and it really genuinely is a little bit of statistics that we did to investigate something associated with a new technique, a new instrument. So let me tell you about that. So Gabrielle said, what is LIBS? Well, that's what it is. Laser-induced breakdown spectroscopy. That is a LIBS machine. It will not make coffee. It will not heat up your sandwiches.
Do you have a scale for this?
Yes, how big is it?
Oh, about the size of a microwave oven, which is why it won't heat up your sandwiches. It, at the very simplest level, is a instrument for determining elemental composition. It's a relatively new thing, so let me say something about that. Oh, I meant to say, I'm not going to talk for very long today, so I know I have a 45-minute slot, but I know that you're all thirsty. I'm not going to keep you from your beer. So it's an instrument that's been around for some time. So the original technique was discovered, invented in 1962. And in the 70s, commercial instruments came on the scene. And it was around about the start of the 2000s that people who are involved in forensic science and analytical chemistry became interested in this instrument. Having said that, the commercial evolution of these instruments has been, rapid is not the right word, but it's an ongoing process, and that's probably going to have some impact on, has had some impact on the results that have been observed in the past and the results that I have here and the results that we might give in the future. So what does it actually do? It consists of generally of a laser ablation unit. So that unit has a laser, as the name suggests, and we zap the sample with it. You focus a very high-powered short pulse laser on the surface of a sample, and it ablates it, it destroys some of that, very small amount, and that gets evaporated up, changes phase into a plasma, so gas, then plasma. And that process of heating up and then cooling down and changing phase again is where, if I understand my physics correctly, is where the visible spectrum is emitted, and it is detected with a spectrographic detector and quantified. So the information that comes out of the instrument is recorded over a set of wavelengths or wave numbers, and it yields a spectrum, not a single data point. Now, in terms of the amount of substance that's ablated, it's very small. So if you have a reasonable quality instrument, you will have a laser beam that's around about 20 microns wide. A human hair is around about 200 microns wide. So there are some great shots of things that are being laser ablated, and you think you're looking at a flute, and it's actually somebody taking shots along the length of a hair. It's possible to do things like that. I really like this instrument just from a sort of a historical point of view, and it kind of has a little bit of a relevance to being here. So whilst as far as I know, Isaac Newton wasn't particularly interested in chemistry, he was definitely interested in optics and light. And the earliest chemists, one of the things they used to do to identify compounds was burn them. They put them and see what colour light was emitted. And this is exactly the same thing, but in a very, very modern setting. I also like to tell people that the early chemists had a habit of tasting every compound that they were testing. So not so good if you've got polonium-210. Maybe it would go down better with a cup of tea, I don't know. But anyway, this is what comes out. So this is a spectra, and that's a single data point. Now, having said that, and one of our earlier speakers alluded this to already, I think John Aston it was, that this is really should be modelled as functional data. Okay, the observation is, in some sense, a curve, although you know might be hard pressed to describe that as a curve. But traditional sort of treatment of measurements like this is that you decompose them and treat them as massively multivariate observations. That works up to a point, but you will lose some information about the ordering of the peaks there. I really like that to happen with this particular instrument. The work I'm talking about today is actually work done by my PhD, Anjali Gupta, and really what she's supposed to be working on is functional data analysis for this kind of signal, but she hasn't quite got there yet. So the ensuing analysis is going to be univariate. We're just going to look at some individual peaks and treat them like they're independent observations, and I'll talk a little bit more about why we decided to do that. So why is it an interesting instrument for forensic science? So I work in a number of fields in forensic science. So I'm glad to not be talking about DNA today, although possibly I could say something to annoy Phil David. That didn't seem to take very much. So I work in DNA, and those of you who know me from way back, or maybe not that way back, Mariana's and I are still very young, know that I started out working on glass. It's interesting to my colleagues who are interested in trace evidence rather than people who are working in DNA. The instrument itself actually can work with any substance. So it can work with gases, it can work with solids, it can work with liquids. The people that I generally work with in chemistry are either ICP-MS people, mass spec people, so inductively coupled mass spec people. Some of my other colleagues have scanning electron microscopes with detectors attached to them that again let them do elemental composition. So it's in that realm. The ICP-MS is, well, depending on who you talk to, but I talk to ICP-MS guys, is the gold standard of instrument for this kind of field, for determining elemental composition. The downside to the ICP-MS, although it's a very good instrument, is that it's very expensive. So Michael can tell me I'm wrong. Somewhere in the 200 to 300,000 US dollars, up to $500,000 for a very modern instrument. It requires a single place to sit. So the LIBS machine, I could actually buy one myself and stick it on the end of my desk. If you own an ICP-MS, you have it in a separate room. It's air condition controlled. It requires the use of exotic gases for the entire time it's operating. So argon, I think, is one of the ones that gets used, and that costs you about $40 an hour just to run the gases through the instrument. And you know, it needs maintenance and needs an operator. So these things are cheap by comparison. About 100,000, 150,000 New Zealand dollars. It's about 100,000 US. You can actually make one yourself if you know what you're doing. If you've got a laser ablation unit and a series of basically lenses, you can make your own LIBS machine. And Jose Almaral, who I work with in Florida, his students have done that, just made it on a table. It's not as good as the commercial instrument, but it can be done. It's portable, so you can take it to the crime scene if you want. Now, I have opinions on whether you should be making measurements at the crime scene or not, but this is the kind of thing that law enforcement agencies seem to be interested in doing, so it is possible with this particular instrument. There's no special sample prep required. So before we had laser ablation units, We used to have to do things like acid digestion of samples. That doesn't have to happen anymore. The samples don't need to be mounted in any particular way. In fact, last time I saw it being used, we were just looking at fragments of glass, and the person I was with just mounted the samples in a piece of blue tack. Right? So that's sample preparation. And it's essentially non-destructive. So you can measure the questioned item a number of times without necessarily destroying it, which is very important from the legal point of view, being able to retain some sort of sample for retesting if the court requires it. Having said that, there is popular wisdom, publications in the literature that suggest that the instrument has relatively poor precision and has problems with repeatability. Now, there are actually pretty good reasons why this might be true or might have been true, and it's something that might be changing over time. But I'd like to sort of leave that discussion to the end of the talk today. So the research question here is very, very simple. Okay, where it's simply going to look at whether the variation in measurements taken on different days is larger than the variation in measurements taken on the same day. So that explains my rather dull title about intra-day variation and inter-day variation. It's an important question. So despite it being a very simple question, it's an important question. And the reason for it being an important question is twofold. Firstly, I talked about the possibility of the court requiring you to retest a sample or set of samples. If you don't have repeatability, then you have no guarantee that you're going to get the same set of measurements the next time you take them. That doesn't matter in one sense. So it doesn't matter if you live in the match-non-match framework. Okay? If your sole mode of interpretation is to say that these two samples match, possibly could have come from the same source, or these two samples don't match, this instrument is really fast. You can take measurements very quickly, so you can take all of your measurements in the same day, and you don't have to worry about this variation, because relative to each other, they should be about the same on the same day. But it also matters if you're thinking about collecting a database. So I said I wouldn't say anything about likelihood ratios. I sort of lied. Of course, if we want to calculate a likelihood ratio, we have to understand something about the variation in the population. And the only way we can get that is through building a database. So there's a standard statistical technique for these types of problems, and it comes from the auspices of formal experimental design. We have a standing joke in our department that experimental design is kind of like Morris dancing. Most of the audience is English, so they're probably familiar with what Morris dancing is. It's a traditional form of dance. It's practiced in the summer in various parts of England. The best of my knowledge, it's an excuse to escape the house and go and get drunk in the sun with your mates. That's never been true for me with experimental design, but you know, I'm working on it. We call it Morris dancing because if you've ever been to a talk on experimental design, very quickly the conversation degenerates into discussions about expected mean squares and how to allocate degrees of freedom, and as Chris Triggs likes to add, the kind of things that should be done between consenting adults in private. So yeah, it's viewed as kind of old-fashioned. That if you look at the sort of the origin of modern statistics, this is what the early statisticians were doing. So this is what Fisher was doing, and this is what Pearson was doing. That they were looking at results from crop trials, which is where experimental design came from. When I teach it to my students, they either fall asleep or they look at me sideways like I'm insane, but they learn enough to pass the exam and then they promptly forget about it. It really should be a mainstay of just about any scientific discipline because it's so lacking in the scientific research that we actually see. So I'm not a big fan of beating up forensic scientists, and I'm not really about to start, but it would be helpful if some consideration was given to these three ideas. So these are Fisher's three principles of experimental design. I believe they're in his 1925 book, so we've had a bit of time to get used to them. That we should employ randomization to avoid bias. We should employ replication. That's just a fundamental part of science, but if you can't repeat it, it's not science, it's not real. And the blocking is perhaps something that's a little bit peculiar to experimental design, that we should take account of or exploit known differences between experimental subjects or experimental units. And just about all of these things are missing in most of the experiments that I see published in the journals. So I said I work with my friend Jose Almaral. I say to him, Jose, I'm interested in this idea. I think I need to do some experiments. Obviously, I'm not the analytical chemist, you are, so can we do this set of experiments? And his response will be, oh yeah, we've done that already. Okay, well that's nice. Can you show me the publication? Oh yeah, I'll send you the publication. So he sends me the paper, and my response pretty much uniformly is, no, that's not it. That's not what I was talking about. That's a communication error on my behalf, that I didn't explain clearly what I wanted to do, but also a communication error from the point of view that what I would regard as an experiment sufficient to explore the phenomena that I want to look at is not the same thing that a chemist might be thinking about. Okay? It's not to say it's a bad experiment, it's not to say that it didn't show something, but there is sort of this prevailing attitude that one experiment can answer many questions, and sometimes you need really specific types of experiments to answer the questions. I talked about these three things being important and being missing. One real common thing to do is to take a control sample or do a control experiment and then look at different treatments, which is, different, the sorts of things that you do in experimental design. But the practice is to measure your control samples or your control subjects once and do the replication in all the treatments. So you've got this sort of imbalance going on when everything should be replicated equally and done in the same way. So I know not everybody's a statistician. We talk about different types of design. So most experimental designs fall into this category, and all it's saying here is that before you carry out the experiment, so the things you're going to experiment on, which are the red boxes there, are identical in every possible way. So we don't think that there are any differences between them, and then we randomly allocate the treatments. In this case there are 4 of them, A, B, C and D, to the experimental units. So a lot of experiments are carried out in that way or analysed in that way under the assumption that this is true. So the next step up from that is when you believe that you have some sort of structure, some sort of known source of variability that you should take into account when you are performing your experiment. And I know I'm teaching statisticians to suck eggs, but I want to talk to the people who don't know anything about experimental design. So a really good example of this is not quite a randomized complete block design, but we take the situation that we have with the 2-sample t-test, right? So, sorry, the paired t-test. So in the paired t-test, that you know that there are differences between the subjects, so you make sure your comparisons are made within each subject, okay? The idea that you're trying to take account of here is that variation within subjects is lower than variation between subjects. So I do an experiment in class where I get all of my students to listen to some very quiet music. They play Enya or some new age crap like that. And then I get them to measure their pulse, and then I play something really loud, like the theme song from Mortal Kombat, and I get them to measure their pulse again. Why am I getting them to measure their pulse twice? Well, we know inherently that pulse rates are different between people, regardless of the experimental treatment. There's no concept of randomization there, but the idea is basically the same. So we are interested in this situation about whether the variation within those blocks is lower or higher than the variation between those blocks. So this is the actual experiment that we carried out. So we took measurements over 5 days 5 days is roughly when we felt that we were sort of getting some handle on the variability. I don't want to say too much about that. We measured pieces of glass, so samples there, from the same source. So 4 pieces of glass from the same source, and the source was a standard reference material produced by NIST. That is a glass with known chemical concentrations, or at least known up to within about 0.5%, is it something like that? 99.5%. Each fragment of glass was measured 3 times a day, so there are 12 measurements from each day over 5 days, yielding 60 observations altogether. And I don't know whether anybody's going to pick this up, but I'm going to point it out. But you might say to me, well, why am I measuring the samples 3 times a day? And in the standard experimental design, I would not have that replication, because that would just be technical replication, right? I would be understanding something about the precision of my instrument rather than anything that had to do with the variability that I'm actually interested in. We had this idea that we would do 3 runs per day, and so what you can see there in the replication is actually the remnants of that part of the design. But we actually decided that this was kind of a strange concept, because when you're thinking about doing 3 runs or 3 batches or whatever you want to do, it's sort of like saying you're taking all of those measurements at the same time, and we actually are not. We're taking those measurements in the sequence that they're given there. So we ignored that part of the structure. I should say that no forensic scientists were harmed in the production of this data. So what do I mean by that? Well, I made my PhD student go to the lab and take those measurements herself. So I wasn't going to waste a full-time forensic scientist's time taking measurements for an experiment that I'm interested in and she's not. So I made Anjali go and do the measurements. I can't overemphasize how important that I think that is for people students working in this field. Familiarity with the instrumentation that you are working with, analysing observations from, is incredibly important, both in terms of just showing some element of respect for the scientists that you work with, but also being able to have a common language. You know, it's through doing things like this that I can bullshit my way through all sorts of grant applications and whatever, because I know the language. I've been there collecting the measurements with the people who are actually talking about doing experiments with it, and they appreciate that I sort of understand what they're talking about. And it also reduces the opportunity for confusion, and it just leads to a more productive collaboration. So here's the statistical model. I promised you that there was very little statistics in this talk. This is about it. The model is very straightforward. It's a standard model for a randomized complete block design. There are fixed effects, and you might say, well, James, you're a Bayesian, you don't believe in fixed effects. That's true, but I'm just going to pretend I'm not for a while. And there are 2 random components, 2 variance components. So one is a day effect, and one is an experimental unit effect, or you can think of that as a measurement within day effect. And they have the standard assumptions that they're normally distributed, centered around 0, and they've got their own variance components. We're not interested in the μ's. We're not interested in the treatment structure of this experiment. You might say, why did I allow there to be different means for each of the fragments when they all came from the same source? It just seemed a more realistic thing to do. We are actually interested in those estimates of the variance components, the sigma d and the sigma e. So if we can get those things and we take the ratio of them and we find that they're less than 1, this basically says we don't have to worry about this problem of inter-day variation being too high, that the instrument is capable of yielding repeatable measurements, and we can do what we want to do. One of the things that I've been concerned about, and I've been talking about for quite some time, is that the statistical treatment of compositional data. And those of you who've been in statistics for a while know that John Aitchison wrote a whole book about this, which was published in 1986. And one of the issues with compositional data is that there's this induced dependent structure that comes from the measurements being a composition. The fact that they might be constrained to add up to a percentage induces correlation, but the fact that there's a finite volume of substance that can actually be measured also induces a correlation. And so Aitchison has a couple of methods that are used to break that dependence. And this is one of them, which is called the additive log ratio. So you choose one element out of the elements that you're measuring, and you use that as a denominator, and you divide all of the other measurements by that value, and then you take the logarithm of that. So it has a nice, and then those transformed variables will be transformed onto a space that runs from -infinity to +infinity, and then you might want to make some assumptions about multivariate normality, and that seems to work okay. It has a nice statistical justification, but it has quite a nice sort of practical chemist's reason for doing it. Maybe not the logarithm, but standardizing your measurements by measurements taken on the same day doesn't seem to be such a terrible thing to do. It sort of puts it on a day-free scale or something like that, and it's something that is kind of done already. So it may not be that the division is explicit, but you do regularly take the measurements of a sort of a reference element and make sure that your observations fall within a certain percentage of relative standard deviation, some measure of reliability of those things. So this is a nice thing to do to the data, and we recommend doing this routinely. Those of you who have read Gregor Zadora's book on dealing with this chemical data know that he also does this routinely for compositional data. So it doesn't make a huge difference to the results, but I still think it's a reasonable thing to think about doing. So there are the results. I've only shown you half of the peaks that we looked at. You will see that I have treated each of the measurements as independent objects, independent variables. I've taken no account of dependency between those, and there are very good reasons for some of those things to be related to each other. So for example, if you are measuring aluminium, it does not yield just one peak, it measures multiple peaks. That's sort of the signature of aluminium. So we've got multiple aluminium peaks, we've got multiple calcium peaks, and so on. If I was really looking at the instrument from the point of view of should we be doing with forensic data, so if for example, if I was looking at glass, I probably wouldn't be looking at most of these elements anyway. Okay, just at the moment I'm looking at things that are in relatively high abundance. When I really look at glass, I'm interested in things that are in very low abundance, the trace elements, because the major components of glass are pretty similar from glass sample to glass sample. There are certain chemical elements that make up glass, and that's it. So why would you look at those things? You want to look at what makes it different, and what makes it different are these little bits of stuff that come in from the geological sources of the components that make up the glass. The other thing about this is, of course, I could have done the randomized complete block design in a multivariate way, but I'm going to put the question out to the statistician. So firstly, how many of you have done a multivariate analysis of variance? Okay, so your p-value is significant. What do you do after that? Do you give up and just say it's significant? I'm going to, Curran, you can contradict me, but I'm going to say most statisticians then turn around and do 10 univariate analysis of variances and report on which ones are causing the difference. It seems to be pretty standard practice. So that's sort of what I'm doing here. It doesn't matter.
Not necessarily what I would do.
Not necessarily what you do. Yeah. Well, I would probably say, why are you doing multivariate analysis of variance? No one believes it anyway, but... So just looking at the ratios, we can see that all of the ratios of the components are less than 1, and that's true for all of the peaks that we looked at. you might say, well, these are sort of sample estimates and there is variability in there. Well, I can look at that in a Bayesian way, and that's what those probabilities are down the bottom. So the probability that the ratio is greater than 1 under certain assumptions for the model. Mostly okay. There are the calcium ones that might give us some cause for concern, but you know, I'm not too worried about it. I just did want to say a little bit about the analysis, because there are some things that that came up during the course of analysis. So the first is that we got some negative estimates for the block variances. So this may be well known, but I still thought it was slightly worth talking about. So the first thing is that the standard moment estimators are not constrained to be greater than 0. So even though you're estimating variances, they're not necessarily constrained to be greater than 0. And so you can get these negative sums of squares or negative variance component estimates. And it's just an accepted fact of computational statistics. What normally happens, well, you might say, I'll just set those to 0 because I don't actually believe that they're negative. I think they're just really small. So that's one way of doing it. You can actually take a slightly more advanced estimation procedure, so maximum likelihood or restricted maximum likelihood, and that's what we did. And we found that if you'd transform the data with the additive log ratio transformation, then REML worked a bit better. And the result of that is that those variance components were then constrained to something near 0. So that's why you saw the 0 on the previous slide. Or you can go Bayesian. So I went full Bayesian. It was relatively easy to do. And initially I found the results a little confusing in that they weren't very close to my maximum likelihood estimates. But when I thought about it, it's actually pretty obvious. When you're estimating the block components, the block variance components, you've actually got very little information. I've got 4 degrees of freedom associated with the blocks. That's not a hell of a lot of information, so there is going to be considerable variability. We also discovered in doing this that the priors matter a great deal for variance components. So from time to time I have looked around through the literature on doing experimental design in a Bayesian way, and there is not a lot out there about it, about what's sort of sensible to do and whatever, but there is in this very nice paper by Andrew Gelman pointing out that the standard sort of thing that you do in bugs or JAGs, these systems for computational Bayesian statistics, is that you assume a gamma prior with 2 very small parameters, small shape and small rate parameters. These are close to being improper priors. They're sort of a generalized version of the scaled chi-squared distributions that are the conjugate priors for variances. And in the field of hierarchical models, they don't make a lot of sense sometimes, which is Gelman's point, that they sort of say things that you don't necessarily believe about the model. And the same sort of thing is true here. But he goes on to test out various priors for these variance components, and makes the recommendation of number 3 there, which is the half t distribution. It's basically just the absolute value of the t distribution. And in our experimentation, what happened is that we tried all 3 of these priors. So options 1 and 2 basically have convergence issues because, again, there's not enough information. They're not behaving very well. Whereas option number 3 yielded posterior means, which were very close to our restricted maximum likelihood estimates. So just in conclusion, we think that we have inter-day experimental variation that is not significantly higher than intraday variation. Using the additive log ratio improves repeatability, and what this although the statistics is very straightforward, what this means is that we can start to think about building databases with LIBS. Now, this is one experiment and it needs to be repeated. I was talking yesterday at dinner with Michael, and he'd done a similar sort of experiment. You might not have thought about it in the same way, but it showed there was a problem. So I said at the start that this is a instrument that is changing over time. that there are various quality instruments on the market, and they have been getting better and better, but the industry in some sense has not converged on one technology. So we heard some questions from Mike before about the differences between machines in different laboratories. I spoke about something similar to this topic in the Australian Federal Police, and there was a gentleman who'd been living in Australia for a long time, but he was from Africa originally, and he pointed out that in Africa that they might have a really cheap instrument that did a really bad job, and it might be a problem. And these things are definitely worth thinking about. So we don't often think about the changes that we might observe between different instruments. I think we should think about it a lot more than we actually do. And even Peter Gill said that you've got to think about the variation that you might observe between different gene analyzers. So the same lab can have 5 or 6 different genetic analyzers, and they will yield different EPGs for the same amount of input DNA. Same is true with this instrument, and there will be changes that are due to differences in manufacture and differences in quality. The width of the laser is definitely an issue. So 20 microns is really good, but you can buy an instrument with a 50 micron spot and so on. So we need to do a lot more work. So that's basically it from me. I don't know how long I blathered on for. Half an hour, there we go. And I'm happy to take some questions if there are any.
Any questions?
Curran.
So I'm a big fan of taking logs, but I didn't quite understand the justification for other reasons. I didn't quite understand the justification that it's compositional, because, and I think you've heard this concern or this comment before, that the trace elements are all tiny, tiny, tiny.
Yeah,
and so the sum of all of them is, what, 1%?
So you've been listening to my friend Jose. He and I don't agree. So I think, I can't find the exact line, but I have read either in Acheson's writing or in those mathematical geologists that basically center their career around his work, that subcompositions are also compositions. So the fact that you take a restricted set of elements that are present in the compound that you're interested in doesn't get you away from compositional dependence. This is the position that they maintain.
If the elements that you're thinking about are reliably sum to something like 1%, then I would agree with you.
Yeah.
I'd be a little surprised if that were the case.
Yeah, and so I mean, I might, as I said, I might justify it in 2 ways. One is sort of appealing to the compositional point of view. The other one is that a lot of technologies like this, a daily standard is measured every day, and at a gut feel, it feels like standardizing your measurements with respect to the daily standard is a sensible thing. And so if we're doing that, then we've got ratios, and you and I both know that ratios aren't particularly well behaved, and so taking logarithms is a sensible thing to do.
I'm just saying, I think that the scale of the analysis makes sense, but not necessarily for the reasons that you gave.
Yeah.
You've got lots of other reasons you can appeal to.
Yeah.
I do have a related question, in fact. So are you sure that it seems that your standardization problem comes from the amount of signal that you get? But are you sure that it's not because of the position of the monochromator? So maybe the wavelengths are not completely correct, so everything shifts, because I suppose that there is a mechanical thing in the optics.
Yeah.
So maybe one wavelength is not exactly what you measured, but it's slightly displaced, so everything moves.
So this is sort of a registration type problem, right?
Yeah. So a problem in X, not in the Y.
Yeah.
One way to standardize that would be to use some standard peaks from, for example, silicon.
Yep.
And then just correct for that. Did you think about that, or? Quite
possible. I'm not working at that level, but I do understand exactly what you're saying. And maybe, do you have any feel for that, Mike?
It's a gut feeling.
Well, you made all the measurements with the same instrument. Do you think that the peak positions would be changing?
It depends on the resolution of the instrument. If the resolution is very high, then small move or small...
The resolution on the instrument is much less than the line widths.
Yeah, but still, you may have... Well, I don't know.
It may be a problem.
It's a gut feeling. Because all the time concentrated amount of signal, but it might happen that it's just displaced.
Yeah. I mean, that registration problem will definitely come into play if we manage to come up with some sort of functional model for this data.
Did you do anything to test the homogeneity of the sample? I mean, we all think of glass as being homogeneous, but minor components over a small area?
So I think, well, sorry, you need the answer first. The answer is no. I think that's a sensible thing for us to be looking at. And I think, there are just lots of experiments that we need to do with this instrument before we really know what it's doing. So I think I told you about this last night, but one thing that was pointed out to me in the Australian Federal Police is that the variability appears to increase with the size of the physical sample. So as that decreases, the variability in the measurements increases. And that's obviously going to be problematic, and I can think about an experiment of how to do that, and I would like to see some other people do that same experiment just to see if we can get a grip on it.
So why, do you have an explanation for why the variances change for the different lines and the different elements?
No. I mean, they're not all on the same scale, but so some peaks are higher than others. So the variability is dependent on related to the mean. But
so I assume that the terminology you were using, you gave the elemental symbol and then the number is the wavelength for that.
Yeah, wave number, I believe so. Yeah.
So if what you're looking at is an emission,
yeah.
So the wavelengths could be the same, right, which would indicate that the difference between the excited state and the ground state for that emission were the same.
Okay.
But for these types of systems, that doesn't mean anything about where the ground states are relative to one another.
Okay.
So they could be like this, and the peaks would still be next to each other.
Okay.
Now you got a real problem, possibly, with the energy fluctuations in the laser, because the temperatures of these plasmas can be 20,000 Kelvin,
Yeah.
right? And they can vary significantly. And so the population of these excited states now will differ with the fluctuation in the laser power, and that will change the intensities of the lines.
Yeah.
So it's just a thought, but it's something that you'll want to be careful of.
I'm not happy with the data that we're analyzing, but it's what the people who own the instrument, Sally Coulson, that's what they're collecting at this point in time. So that's where we started, but I think that we've got to be thinking a lot harder about what we really should be measuring. And I would just agree with you in that, my reading, the inability to control the plasma in any consistent way from day to day is one of the reasons why people think that there's poor repeatability between measurements taken on successive days. I should point out that we've got a much bigger experiment now going over 5 weeks with many more sources of glass, and I'm curious to see whether we will be able to replicate the results from that.
Very, very interesting.
One question. Well, I have one extra. So you are modeling this range of standard deviation, which I suppose that if they come from the same population should follow the F distribution.
Yeah.
Have you tried when you align I suppose that when you go Bayesian, you want to suppose what happens when they don't come from the same population, and then have you thought about modeling these with a non-central F distribution instead of?
So I think
I missed that.
I think I can answer this question. So I made this statement that the sample estimates are all statistically significant. What does that mean? It means that they all exceeded the critical F for that.
What's your size effect then? Because they're statistically significant, then should have certain amount of difference.
Yeah, probably. I didn't look at it explicitly. Sorry.
Okay. No more questions?
Your time? I think so.
There's still some time.
Not a question, just a kind of a comment. One of the cool things about this instrument, you can take the laser, expand it, put it through a telescope, refocus it, the distance,
Yeah.
create the spark, collect the data right back through the telescope. And you can do this at a distance,
Wow.
which is a kind of a cool idea.
Yeah, that is.
They can analyze what happens in the moon.
It's a better way to analyze explosives, I think.
Thank you.